Hello, in this session we're going to be looking at correlation and regression. This is going to allow us to explore the association between different factors, different variables that we're looking at. And with regression, start to predict one factor dependent on another factor. So, in particular, we're going to be looking at correlation, Pearson's R and Spearman's Rho, which are looking at parametric and non-parametric data. So parametric would be normally distributed data, non-parametric is data that isn't normally distributed. And we're going to be looking at regression along with R squared and effect sizes, which are really, really important when writing up your stats. And then we're going to try and attempt to replicate a very controversial paper by Stoet and Geary. And we're going to look a bit at standardization and Z values in that. So, when we're looking at the use of statistics, we've done a couple of things in these sessions. We've been summarizing data and making descriptive data with means and modes and medians and so on. And that's pretty straightforward. We're doing a lot of that. You've also been looking at comparing groups and the difference between groups with your t-tests and your ANOVA and so on. Today we're going to be going down this little line, which is looking for the strengths of associations, trying to relate variables to each other, look at the associations between variables. And this is a form of inferential statistics, and as I say, we're looking at correlation and regression. So, what is correlation? Let's start off with correlation. It's going to look at the relationship between two variables to see how strongly related two variables are. And we're going to see some nice graphs in a second to visualize this. And it does allow us actually to do more than two variables in the correlation, but we're going to be focusing on just looking at the correlation between two variables. So, the correlation coefficient is the big number that we're going to be looking for. This is a number that can range from -1, which means they're negatively correlated, to 1, which means they're perfectly correlated, and 0, which means there's no correlation between the two things. And the direction is obviously indicated: -1, negatively correlated, 1, positively correlated, and 0, no correlation. And this is just an example up here. If we had some factor over here on the y-axis and some factor here on the x-axis, and you put the dots on the line, you would think, well, actually, we could draw a pretty straight line through there, line of best fit, and we've got this correlation coefficient of 0.88. So they're pretty strongly correlated, the y and the x values on here. So we'd say that it's positively correlated. And when one changes, the other one changes, and they change in the same direction, which means when one gets bigger, the other one gets bigger as well. For example, if you spend time running on a treadmill, you're going to burn more calories. So the more calories you burn, the more time you've been on the treadmill. The more time you've been on the treadmill, the more calories you burn. And you'll note there that maybe you could burn calories without being on the treadmill. So then maybe it doesn't really mean one is causal, but there is a correlation here. And the taller people are, the larger the shoe sizes. And smaller people will have smaller shoe size. So if you see somebody who's quite tall, you would predict that that person is going to have pretty large feet in general. So that these are forms of correlation. As one increases, the other generally increases too. But we're just looking at the association. Again, we don't want to say that one is causing the other, because this model doesn't allow you to say that. So negatively correlated, you can see here, as the x-axis increases, the y-axis decreases. And as the y-axis increases, the x-axis decreases. So this is called negative correlation. If you drew a line, it would be a line going that way. And for example, as a chicken gets older, it produces fewer eggs. If it's darker outside, more light is needed inside. So the light outside, if the light outside goes down, the light inside goes up. If the temperature decreases, more heaters are purchased, so you might be working in a shop. So if the temperature increases, you don't need to buy so many heaters, but if the temperature decreases, you will buy more heaters. So this is a type of negative correlation. And there are a couple of other examples of correlation here. You can see a line there that's -0.91, that's plus 0.88, we've seen that. This is not so strongly correlated, but you can probably think, well, if I drew a line of best fit, it would go somewhere in the middle there. Again, it's positive, but it's much weaker than that correlation there. And this one here, well, there might be a correlation, but it's incredibly weak. And there's a way of reading these numbers in a second to define whether something's strong or weakly correlated. So we have to be careful though, because sometimes we might get correlations which are spurious. And there's a lovely website called Spurious Correlations. Go have a look at it. The link is on the slides if you just click on there. And you can go and look at some things that seem to correlate, but they don't. You may think, well, maybe that's not they correlate, but are they actually causing each other? So, for example, here, the divorce rate in Maine is linked to the per capita consumption of margarine. Now, you might say, actually, the more that's, what have we got here? So we've got if the divorce rate goes down, which seems to be the case, that's I suppose a good thing. Then the rate of margarine consumption goes down. So maybe people who are married have more more margarine, or the other way around. So there might be something there, but it does seem a bit of a spurious correlation. And then you've got spending on science, space and technology, and suicides by hanging, strangulation, and suffocation. It's pretty certain that those two things aren't related, but as one increases, the other seems to be increasing as well, which seems very strange. And then if you go here, number of people who drowned by falling into a pool and filmed by Nicolas Cage, again, it would be pretty hard to relate those two together. So these are called spurious correlations, and you may have a correlation factor which says they're strongly correlated, but actually the causation is lacking there. So when you read correlation factors, you've got to add a little bit of your own thinking to it to try and work out why the two things might be correlated. And we're going to look at regression in a bit, which is maybe a better way of modelling these things. So correlation does not tell us that changes in X are due to changes in Y. It just tells us how the two are related. We're going to have a look at regression in a moment, which is going to allow us to actually take one value and look, well, if this value changes by this much, then this value is going to change by this much. Regression allows us to do kind of clever, interesting things like that. So correlation only really tells us that two variables are somehow linked. It doesn't really tell us why they're linked, and it doesn't tell us if it's a spurious link or not. And often it's used as a prerequisite for other analysis. So if you find a correlation, you may want to go and throw some regression at it to go and explore it a bit further. Here's another kind of quite famous example. If the wind blows, the trees move. If the trees move, the wind blows. Which is it? So correlation might suggest a link, but it doesn't tell us anything about causation. So let's look at the two different ways that we could be building statistical models to look at correlation. There are different correlation coefficients that you can use. Generally, you're going to be using Pearson's R. So Pearson's R is a correlation coefficient that works on data sets which are normally distributed, or we'd say parametric data sets. And rule of thumb is any data set that's 30 or more items, which for PISA and for DFE data is going to be pretty much everything that you do. The Spearman's rank order correlation coefficient, or Spearman's rho, is going to work on smaller data sets that's non-parametric, so that's not normally distributed, and we can test the data in a second to show you how this works. And so what Spearman's rank does is it takes both variables that you're looking at and it actually puts them in rank order. So if you had a bunch of grades, it would actually put them in the order that the grades appeared. So the A's would be first, then the B's, then the C's, then the D's, and so on, rather than giving you any sort of numeric value. It's going to be putting them in the rank order. And it's going to then compare the ranked order of both those variables, and it's going to give you a slightly different response in most cases. Both Pearson's R and Spearman's rho will give you a value between -1 and 1, and as we saw earlier, 1 is going to be positively correlated, -1 is negatively correlated, and 0 is going to be no correlation. So, what does this look like? Let's have a look. Now, so say kind of 30 is the magic number. If you have 30, you can generally use Pearson. And I should also mention, there's also Kendall's tau, which we're not going to be covering today. But if you do have non-parametric data, non-normalized data, non-normal kind of curve data, like you would use for Spearman, and you've got many scores of the same rank, you might want to use Kendall's tau, but that's not something we're going to be covering today. So here is an example of perfectly correlated data. As one increases by 1, the other one increases by 1, or one increases by 10, the other one increases by 10. This is going to be a Pearson 1 and a Spearman 1. They're both quite happy with that. The rank of both items and the actual value of both items makes the same graph. If we go over here, though, you can see that the data is kind of S-shaped. So with Spearman, well, the line of best fit isn't forming a straight line through the data items. So it's correlated, but not as strongly correlated. Sorry, Pearson's not as strongly correlated as it is for Spearman. So Spearman would actually take the rank of each of these dots, and it would, if you were to plot the rank of each of these dots, you get something very similar to this. So Spearman for this would say it's perfectly correlated. Well, Pearson's going to say that it's actually a pretty strong correlation, but not perfectly correlated. And again, you'd only use Spearman if the number of dots was less than 30 and the data was not of a non-parametric. So other things here, this data here, which is very messy, Pearson and Spearman agree. This data here, perfectly negatively correlated. Pearson and Spearman agree on that. And then again, you've got this kind of weird data set, kind of curved data set. Pearson, negative correlation, pretty strong. Spearman, again, if you use the rank order of these dots, you're going to get pretty much a perfect negative correlation. So pick which one you want, but most of the time you're going to be using Pearson. So how do we go and interpret these correlation coefficients? Well, anything over 70 is a very strong positive relationship. 0 is obviously there's no relationship. You've got no or negligible relationship for the smaller numbers, and so on. So if you're going to go write this up, you're looking obviously for the bigger negative or the bigger positive values to report on correlations between things. And yeah, when you're writing up, just make sure that you're using this sort of language. So let's go have a look at a demo and see how this works in R. So let's have a look at how we can explore correlation through R. Well, first of all, I've got my big PISA 2018 dataset. We can see that we've got 611 to 612,000 entries in here. What I'm going to look at is I'm going to just reduce this down to United Kingdom students who've got the maths, the reading, and their gender. Okay, those are the only fields that we want to have, really. So if we go and run that, I will see core data. Yeah, I've just got the maths, the reading, and the gender for each of these items, which is quite nice. Now, you may want, before you get into correlation, just plot things. So what I've done here, I've got the data, I'm looking at the maths and the reading. I'm going to plot the maths on the x-axis, the reading on the y-axis for each student. I'm going to have points with alpha, so they're going to be slightly see-through, and I'm going to add a smooth line to see what the line of best fit is through this data. So it's going to give us a feel for the correlation of this data. If we go run that, it takes a little while because we still have quite a few thousand students, and there we go. So we've got the PP1 maths, PP1 maths on the x-axis, PP1 reading on the y-axis, and each of these dots is going to be a student, and you can probably feel that there's a relatively strong correlation here. And going back to what we were saying before, we've got more than 30 items, so it's likely we're going to be using Pearson's R for this. So to go and run a correlation test, what we do is we say core.test, and then in this we are going to just specify the first item we're testing and the second item, so the x-axis and the y-axis. So if I go to my core data, there's my core data. I'm going to take the x-axis of maths, and I'm going to say core data, and I'm going to take the reading score of that, so that's okay. And then what I'm going to do, I'm just going to make sure that I've got my method in here. You don't have to do this because I think it defaults to Pearson, but I'm going to make sure it's doing Pearson. So we're going to do a correlation test with maths and reading using Pearson, and we run that, and it comes up with this nice score here. So let's have a look at this. It says Pearson's product moment correlation, which is what we're looking for. The data is maths and reading. The p-value, so it gives us a p-value. So it tells us that we've got a p-value here of less than 0.001, which means it's it's a significant result. We've got a degrees of freedom, which tells us roughly how many ways this data could have varied. So it's roughly the total number of items minus 1. So we've got 13,000, 14,000 students in total that we're looking at. And the alternative hypothesis, true correlation is not equal to 0. Well, we have a 95% confidence interval. So we're 95% confident that the correlation for this data set lies between 0.77 and 0.79. And the actual Pearson R value it's giving us, the core value here is 0.78, which, if we remember, is a really strong correlation. If I go back here to my graph, so 0.78, it's a very strong positive relationship, which we're kind of expecting. Because if we're looking at this data, what's it telling us? Well, it's telling us that the better the maths grade, the better the reading grade. So generally students who do well at maths are doing well at reading, or the other way around. We're not quite sure what the causal relationship is here, but there does seem to be some sort of association between the two values. So let's have a look at how we can use Spearman's row in analysing our dataset. You can probably tell here I'm working quite hard to find a subsection of PISA 2018 which can apply to Spearman's row. So generally we'll be looking for a subset of PISA 2018 with fewer than 30 entries. And for us, it's UK students who are female who have fathers who are cooks. So it's quite a niche group really. And what we're going to be looking at, we're going to be looking at their attitude towards learning, and also the wealth of the student to see if the two things are at all related. So if I go and make this a subset of data, you'll see here that I've got 22 items with various students looking in various ways. If you look at this already, I'm not sure there's much going on there. We might plot this, but let's just use another test to check to see if it's a parametric or non-parametric. So does the data form a normalized form? We can do this by using the Shapiro-Wilkin test. And the Shapiro-Wilkin test runs a little bit like this. So we're going to say Shapiro.test, and then it's going to ask us what do we want to go and test. Well, for us, it's going to be the subdata, and we're just going to go and test one of the fields to check to see. Now, the Shapiro-Wilkin test is a little bit strange because if we're looking for a if the response is a value over 0.05, if the p-value is over 0.05, that suggests that the data is normalized or is normally distributed, I should say. So if the p-value is less than 0.05, then we can assume that it's not in a normal distribution, and we will have to use the Spearman's row test on it. So let's go run that. And if it comes out here, we actually have a value here which is less than 0.05, which means we cannot use Pearson's R on this if we're doing correlation. We're going to have to go and use Spearman's. Fortunate, isn't it? But as I say, I'm working quite hard to get this subset. And if you're collecting your own data from, say, 25 students or 25 persons or teachers or something else, then do this test to check which form of correlation you can use. So here's my Shapiro test. I'm quite happy with that. I now need to go and build my correlation, but to get it to do Spearman's rather than Pearson. So we do core.test, as hopefully you remember, and then we're going to pass it the two values that we're going to be looking at, which for us is going to be subdata dollar attitude towards learning, and subdata dollar the wealth of the student. And down in method, we're going to say, well, I want this to be Spearman rather than Pearson. So if I go run that, we'll then look at the rank order against these things. And what do we have? Well, we've got a p-value here, which is non-significant. And you can see that the Spearman's row is actually quite low. Going back to our table again, it's in the weak positive relationship mode. There's a weak positive relationship, but they don't believe that it is of a significant value. So you can basically ignore the relationship, which, if it's of interest, females in the United Kingdom who have fathers who are cooks, there is no significant relationship or no significant correlation between their attitude toward learning and their wealth. So it doesn't matter how wealthy you are, it doesn't matter what attitude towards learning is, these things don't seem to relate to each other. Whether that's of interest to you or not, I don't really know, but you can hopefully see how we can use Spearman there instead of Pearson. And you may think, well, actually, we've got these, this text here is quite bulky. If I go and run the model that we had up here as well, going on this correlation test, that correlation test is quite bulky. I can't really see myself writing that in a paper. What I'm going to do is I'm just going to push this correlation test, this Pearson correlation test, into something called MDL. So we're going to have a new object called MDL. If I go run MDL, you can see, okay, brilliant. It goes and displays it on the screen. But how do I go and write that in a paper? Because it's very clumsy. There's a lot of text there. And what you can do over here, you can see a list of 9. You can actually explore this if you wanted to. It's loading slowly. Here we go. So you've got various statistics. There's a p-value. If I click on that, it tells you how to extract the p-value from the model. I go back here and I run model p-value. Does it allow me to display that? That's fine. It's 0. We're pretty happy with that. But there is a way of actually starting to display this for reports, and we can use a kind of easy stats, easy reporting on what we're doing. So if I go run that model again, okay, we know we've got our big long model with lots and lots of lines here. It's a bit confusing. I want to go and put this into a paper. What I can do with easy stats, make sure it's loaded. So you run the library, it's happy. You create your model, it's happy. You just click report model, and then it goes and writes the sort of text. And you can just copy and paste this into your paper or into your report that you're writing, which is a really nice way of simplifying the write-up of correlation. And we're going to see this again very soon with regression as well. Okay, let's go back to the slides. Let's look at what regression is. Now we've finished correlation, we're going to look at another type of inferential statistics called regression. Regression involves something called R-squared effect sizes, which also apply to other forms of statistical analysis as well. And it's a very important concept which we're going to be focusing on when we do look at our regression results and trying to read them. So first of all, what's the difference between correlation and regression? Well, there are some similarities. We know that they're both types of inferential statistics. We know that hopefully they with correlation it gives the direction and strength of a relationship between variables. That's exactly the same with regression. And the difference is when we look at what regression can tell us about these variables. Regression allows us to predict one variable given another variable. So the change of one variable, what would that then result in terms of the change of another variable? So it's not just a relationship, it's actually telling us a little bit more about the predictive value of one variable compared to another. So correlation is effect only, while regression offers a certain form of cause and effect. With correlation, if you were to swap the items round, the x and the y, you'd get exactly the same result. So maths predicting reading is the same as reading predicting maths in correlation. Sorry, I shouldn't say predicts. Maths association with reading is the same as reading's association with maths. With regression, it's actually one way. So the maths prediction for reading is going to be different from the reading's prediction for maths. With the example I've got here, education affects home income differently from how income affects education. And with correlation, you get a single number, a single point, a single value, while with regression, we are starting to work with lines of best fit. I'm going to talk about how these equations are constructed. So very roughly, what we have is we have a dependent variable and we have one or more independent variables that predict the dependent variable. And here our independent variable is a cause of the change that is independent of other variables. So these have to be independent of each other. So if you have height and weight, that's okay, but if you have height in centimeters and height in meters, they're going to be linked to each other. So we can't have the same thing repeated twice. They have to be independent of each other. And then the dependent variable is the effect of the cause. So the cause is over here and the effect of the cause, so what's changed is over here. So if we change these, one of these or both of these, what's the actual impact on this thing over here? That's what we're looking for. For example, little models we could have maths grade given the height of a student. There might be something about age, and the higher you are, the better you do at maths because you're older. Or there may be no relationship at all with that. We've got attendance given gender and wealth and some sort of cognitive test. And then what we can do, if we've got multiple items over here, we can start to isolate them. We can say, what is the impact of gender on attendance if we are controlling the wealth of a student and the cognitive ability through a quite crude SAT score. So we can start to, I suppose, isolate the impact of each of these variables on the dependent variable. Or we could have physics grade given the maths grade and the gender. And again, what you do is you say, well, we're going to control for the maths grade. So hypothetically, we're looking at a student that's got the same maths grade as another student, and then we're going to see if gender actually impacts the grade. If we control for maths grade, what does gender do in terms of predicting our physics grade? We're going to be looking at some of these examples very soon. So, what is regression? Well, it's the relationship between one dependent and one or more independent variables, hopefully, as you've just seen. We're going to predict a value from one variable, and we're going to predict the value of a variable given other variables. And we say it's a hypothetical model because it's a model built on the data. It doesn't mean that it is, I suppose, a true reflection of reality, but it's a reflection of the relationships between the data in that particular model. And we use a linear model. It's what we're going to be looking at, something called linear regression or linear modeling, and you have all your data points, and pretty much you put a line of best fit through, and then when you describe that line of best fit, you can start to play around with the variables and to see what happens if you were to change one variable. How does that change the actual outcome? And if you want to get into your maths, it's a bit like this. We've got the outcome given a constant and a parameter. Given a constant plus a parameter and predictor. So the constant here would be our intercept, which would be 5 on this particular graph, and then the parameter and the predictor. So the parameter would be our beta value. This would be what you multiply your predictor by, and what you multiply your predictor by. You have as many as you want on this side. And we have, just to give you a bit of background on graphs if you've forgotten, so again, over here is our intercept, and these lines here all have the same equation, but with a different intercept. Okay, so the impact of the slope of these lines will be the same, but it's going to have a different intercept. And here, as you can see, one is a positive slope, one is a negative slope. So if you get one of these lines, we can use the predictors to predict the outcome of our model. We use the independent variables to predict the dependent variable in our model. So what it's doing to go and build one of these lines is it's actually using the method of least squares, and you basically have all your points. You're going to put a line going through all the points where the distance between these lines is the smallest possible. So if you look over here, well, the distance between these lines, it's all negative, so the line is in the wrong place. In here, it's right in the middle, with pretty much that one cancels that one out, that one cancels that one out. So it's the line of best fit is the line which goes through all the points where the distance between that line and the points is the smallest possible, and that's what regression basically does. It goes and builds that line for you, and we call these points residuals. So when we're building our linear model, we want to make sure that the variables should be continuous. There are ways around this, so we can use things like gender. For example, in gender would be coded as 0 and 1. It's not quite continuous, but there are ways of kind of faking the continuous data if you need to. We need to have an absence of outliers, so we shouldn't have a big chunk of data somewhere and then all the other part of the data is in another part of the graph. It's a linear relationship, so we're going to draw a line of best fit, as you've just seen. Independence of observations, as I've mentioned, we need to make sure that each of the independent variables is actually independent of each other, so you don't want to have your height and centimeters together, because they're going to be linked to each other. And if you're doing multiple regression, and this is a regression with multiple independent variables, you need to make sure the independent variables aren't highly correlated with each other, which again makes sense. And I've actually misread that one. So independence of observations, you need to make sure that you've got each observation, each point on your graph needs to be a separate point rather than a repeated point. So you don't want to have the same person in the same data set multiple times. Each person in your data set should be in the data set one time, if you're looking at students, for example. So we are going to show these graphs in a second. We're going to try and read these graphs, but there's a really important concept that we need to be aware of, and that's around effect size. And there's a really interesting paper if you want to read this. It's called "It's the Effect Size Stupid" by Robert Coe up at Durham. And very often when we talk about statistics, we're looking for those p-values, and as you know, a p-value needs to be less than 0.05 for us to think that the result that we're looking at is significant, and that's absolutely valid. But you might get the same p-value or very similar p-values for two different experiments. So we've got experiment A here and experiment B. Now they're both significant, but you would probably, I hope, look at A and say, well, actually, that's more important, because if these, so you've got your control group, and then you go and apply something to the control group, and this is the outcome. Well, the outcome in terms of the distance is the same, but in terms of the graphs, this graph is very different from this graph. There's not very much overlap between the two. So we would say the effect size of A is much greater than the effect size of B, because even though the movement's the same, what's happened is there's a huge overlap between the two data sets. And the more difference between the outcomes, the better, basically, because that's going to show that whatever you've tried to model has had a bigger impact on the final result, a bigger impact on that dependent variable. And this is what we're talking about when we're talking about effect size. So we've got R and effect size R squared. We've already met R on its own. We've met Pearson's R, and the correlation between the correlation value can also be called the R value. But what we're going to do when we're talking about our regression models, we're going to be looking at the R squared. So we take the correlation and we square it, and that is going to tell us the proportion of variance accounted for by the model. And we can read this quite easily. If you have an R squared value of say 0.46, it's explaining the variance. 46% of the variance would be explained by the model. So R squared is another way of talking about the data. It's a nice way of talking about the data. You've also got adjusted R squared. People tend to use these interchangeably. Some people prefer R squared, some people prefer R squared, adjusted R squared. It depends on where you're trying to publish, and often they're very similar, which you're going to see with some of our results very soon. So how do we interpret R squared? A bit like we had the nice table for interpreting correlation coefficients. These are tables for interpreting R squared. Now, this is going back some time, but it's quite a common thing to use nowadays. You've got Cohen in 1962 talking about effect size of 0 to 0.19. Pretty much you can ignore that. What if you see 0.2 to 0.49, it's small, 0.5 to 0.79, it's medium, and 0.8 plus, it's large. Excuse me. So those are our effect sizes, but you'll notice over here, this is actually what the Education Endowment Foundation uses, and they use a slightly different model. And for education research, it's very common to get very low effect sizes. So the effect size is talking, for the Education Endowment Foundation, they've tried to convert this to months progress. And if you've seen the Education Endowment Foundation's teacher kind of evaluation toolkit, you get this. So you've got the kind of intervention that you look at. So it could be performance-related pay, reading comprehension strategies, metacognition, self-regulation, and how much would that cost for a school to implement, and what's the evidence base for it being successful or not. And then over here, interestingly, is the impact. So they're saying this is a number of months impact. If you were to implement performance-related pay, you would get an extra month of progress for every student in your school, if you're reading this in a naive way. And that's what people are using this for. They're saying, well, we need to performance-related pay because it's going to give us an extra month's progress for our students. If you go and look at the actual table that they're using, well, 1 month's progress is here. So 1 month's progress is 0.02 to 0.09, which, as you can see, they're saying is low impact. But over in Cohen's basically saying you can pretty much ignore that. And that's a little bit worrying because we are basing a lot of interventions going on in England and around the world on this reading of the toolkit, and the effect sizes they're using in other fields might be dismissed, but for education we generally go with smaller effect sizes. We're happier with smaller effect sizes. And also, I should note, in the Education Endowment Foundation toolkit, it's not just one study that they've done multiple studies on these things. So when you look at 4 bars of evidence here, they will have looked at probably dozens and dozens and dozens of studies to show that this is good, and then they go and get the average and see 7-month improvement. That's 5.3 to 6.1. 5.3. That's a medium effect size. So that would be pretty pretty well received by Cohen back in '62, and probably pretty well received by us now. But when you get to the margins down here, it does get a little bit more difficult. And actually, if you go back in the Education Endowment Toolkit a couple of years, they had learning styles giving an effect size of 1 month. It was considered to give an effect size of 1 month, which is a little bit weird because we always talk about it as a neuro myth, learning styles being a neuro myth, but they thought they had evidence for a month's progress on that a couple of years ago. You need to go and read the papers behind that, of course, because there'll be nuances to that data. But it's something that's completely dismissed now, and actually the current toolkit has it as 0 months. It doesn't seem to have any effect at all. Okay, so how do we go and read these things? Well, this is actually a publication that I put together a couple of years ago. And what you have is you've got every single subject in the English curriculum at GCSE level, and you've got a model over here which is the outcome in that subject, the grade in that subject, given the average grade in the other subjects and the gender of the student. And over here what we can go and see, we see the stars, we can see that actually both of those things are significant for results in computer science. I'm going to pick on computer science. And you can see here that average grade, so one grade if your average grade was one grade higher, then you would get 1.22 more grades in computer science. So the predicted value of an average grade, if it went up by one grade, it would result in the model of increasing the computer science grade by 1.22 grades. Now, if you then controlled for the average grade in the other subjects, you can look at the impact of gender on its own, which is quite interesting. And you can see that if you control for the average grades in other subjects, so a very naive way of controlling for ability in other subjects, you end up with gender predicting 0.31 of a grade in computer science. So this is actually males doing 0.31 of a grade better in computer science than females. And we're going to be looking more detail about this, the gender gap between males and females in STEM a little bit later. And you can see the other things we're looking down here. So this is 0.31. This is the estimate. The actual effect size of this model is 0.61. So if we go back to our Cohen 0.61, we're in medium effect size. If we go to our EEF 61, we're in high impact mode. This is quite good. This is actually a model that explains a lot of the variance. So if you want a good model for explaining the variance in computer science grades, looking at average grade in other subjects and the gender of the student explains about 61% of the variance in terms of what we're looking at. Here's another example from the same piece of work where I was trying to look to see if the poverty of a student would indicate whether they would take computer science or not. And you can see here, well, we've got a really good p-value. So this is our p-value, which is pretty much 0. So this is a significant finding. And we're looking that, the poorer the student gets, the more likely they are to take computer science if they're a female. So you can see this little bar going upwards. You think, okay, that's very interesting. So the poorer the student, female student, the more likely they are to take computer science. But then we're going to have to work out our squared up here, and you can see it's incredibly low. Even that's even dropping off the level we got for the EEF. So unfortunately, we have to say, well, not very much of the variance is explained by this. It's it's interesting, but because the effect size is so small, it's not really something we can go shouting around about. But I suppose if you were to work on this model, so instead of just taking CS, give an IDACI score, and to throw some other things in there, you might find out that there are models which have a higher effect size, which you can then start to publish. But certainly for this, this was interesting because the effect size was so small. Let's take a look at how we can report linear regression. So we have this piece of text here which you might find in a report. It says the number of sales was predicted. It was found that expenditure in adverts, beta 0.578, p less than 0.1 was a significant predictor. The overall model fit was adjusted R squared of 0.331. A couple of things here. So beta is our estimate value that you saw in the previous slide. And it would be per unit of advert. So units of advert could be every £1,000 of advertising that you spend, you increase the number of sales. And again, number of sales might be in thousands too. So 0.578 of 1,000 sales would be increased every time you spent £1,000 on adverts. So basically, the model suggests that every £1,000 extra you spend on advertising, you're going to get another 578 sales. People going to buy that record, and it is significant as the p-value is so low. And then we've got the adjusted R squared of 0.331, and that's going to tell you the variance of the model. So 33% of the model variance is explained by by just looking at advertising. So if you want to predict the number of sales, 33%, a pretty good R squared value, is predicted by the just looking at the spending on advertising. So that's a pretty good model if you were working in sales for records. So let's go and look at some PISA results now. This is what you'd get when you go and run it, and we're going to have a look at in a second to see how this works. So you've got your formula up here, which is maths predicted by reading and gender. And we saw earlier that we have to have continuous data in our predictors, well, actually we can turn gender in a way into a continuous value by actually coding it with numbers. We're going to see how that works in a moment. So in our coefficients table, we've got the estimate or the beta values over here. We've got two of them, one for reading, one for gender, and we've got the p-values over here, and you see they're both highly significant. So we should pay attention to both these things as predicting math results. I mean, I suppose the interesting thing, if gender didn't actually impact math results, that would be more interesting, because then there wouldn't be any difference between gender. But this is suggesting that there is a difference between gender if you already consider and build into your model the reading grade. And that's, I suppose, a little bit concerning, because we are here looking again at differences in genders for the results in STEM. So the first line, we've got the reading grade, and you'll notice it's written this weird way, minus 0.1, which means we're going to pop the decimal place 1 to the left. So reading, if you control for gender, so let's ignore the gender, we're going to just look at, when the model doesn't have to consider gender at all, we've got the reading grade predicting 0.82 of a grade in maths. So it's a pretty good, an increase of one reading grade is going to increase the maths grade by 0.82 in our model, which again sounds pretty reasonable. They're pretty highly correlated, and you'd expect something like that. More interesting, I suppose, is this line here. So we have gender female being coded as 0 and gender male as 1. So if you increase gender from 0 to 1, from male to female, then what happens is you're going to see the grade in maths increase by +1, so that's going to be by 27.98 grades. Okay, so we have the average grade around 500, but that still seems pretty substantial. So if you control for reading grade, you've got girls and boys with pretty much the same reading ability. You're going to see that gender, just being a male, is going to get you a higher maths grade. So it's looking likely here that in the whole data set, males are generally doing slightly better in maths if you control for their reading grade. So that's hopefully pretty straightforward. Down here we've got degrees of freedom, which is telling us that we have about 606,000 students that we can perform this model on. We kind of know that. And then you've got your R-squared down here. As you can see, it's the same for adjusted and the same for R-squared. They often are the same. And this model, so in terms of maths outcomes, the variance of maths outcomes, 70% of that is explained by this alone. So that's a really good indicator that this is a good model for predicting maths outcomes. And as you would probably predict, it would be with reading thrown in there too, because we saw those were highly correlated earlier. So that's enough talking about what all this stuff means. We need to get on to a demo. Let's take a look at how we can do regression in R. So we're going to be using a linear model, and to get a linear model, we just type LM into R. And LM stands for linear model. And we have this structure here. So dependent variable, tilde, independent variable, plus independent variable, plus independent variable. And we need to define the data set. So the data that we're using is going to be PISA 2018. And then we're going to just define the fields that we want to use from PISA 2018. A simple one would be testing out, can we predict a maths grade only given the gender of a student? And if I go run that, the results, it's not quite what I wanted. I was hoping to get a bit more than that. We can see that the gender seems to explain 3 marks or 4 marks in the math score, which seems very low. But this isn't the model that we've already looked at. What we need to do is we need to go and I will just put this into an object called MDL, and then what we'll do is we'll say summary MDL, and that's going to give us a summary picture of what this model looks like. And now this looks a bit better. So we've got the model that we're talking about, maths given gender, and then we can see that male, so this is the student, again 0 being female, 1 being male. What happens if you change the variable from female to male? The estimate is 3.8 increase, so which means males are going to go slightly higher. It's a significant finding, which is good, But then you go look at the R squared and it is abysmal. It's absolutely tiny. So we can say that yes, there's a significant finding here, but the effect size is so small, it explains almost none of the variance in the model. So gender is a really bad predictor on its own for looking at math score, which I suppose is quite positive in a way. So let's go and look at make the significance any higher. So with this model, I'm just going to go and replace that with PV1 science. I would imagine that science would be highly correlated with maths, and it should be a pretty good predictor. So let's go run that again. So you can see here that science, for every increase of 1 science grade, you get 0.86 of a maths grade. That's significant, and actually the R squared value is really high. 71% of the variance in the maths score is explained by the science score. Again, that's good. So the R squared value is a really positive thing there. So science is a good predictor of maths score. So this is our simple regression model. I'm going to try and do something a bit more complex. So again, we'll have MDL, and it's going to be a linear model. And I'm going to try and predict the math score, PV1 math, and I'm going to I'm trying to improve on my gender model really. So let's go pull gender down again from the top. I can never remember what it is. There's our gender model, and obviously our data equals PISA 2018. And if we go to summary of the model MDL, we can see run. Okay, we get the same model up there. So we can go and add some other things to our model. If we go to plus at the end, I'm going to add the wealth of the student. So if you control for the wealth of the student, does gender actually have an impact on how students do? So we go run that, and you can see, hooray, the R squared's shot up. It's nearly at 0.1, which, as we've seen from the Education Endowment Foundation, they would quite like a 0.1. I think that would be quite acceptable in terms of what they're trying to publish. So we can see female to male is now explaining slightly different. The values change. When you put wealth into the model, the actual estimate or beta values change for different items. And this is quite exciting. So once you control for wealth, we can see that actually males now only account for it's 2.95 of a grade. Okay, so that's a very, very small factor that males increase. Wealth-wise, well, the richer you are, you get a much higher grade, which we could probably predict on that too. I forget what the units of wealth are, but it seems to be a better predictor than being either female or male. Okay, so we can go and add something else to it as well. Let's go and add to wealth. We can add what should we have a look at? Well, the number of minutes learning maths. You would imagine that to have a really big impact on your outcome in maths. So the more time you spend in school learning maths, the better you're going to be doing at maths. It makes sense, right? So let's go on that again. What do we get? Okay, so the number of minutes learning maths. So for every extra minute learning maths, you get 0.006 of a grade in your maths score, and that doesn't seem great to me. So the number of minutes learning maths isn't great, and also you'll notice down here the R squared value is worse. So this is a worse model for explaining the variance than just wealth and gender on its own. So the number of minutes learning maths doesn't seem to be explaining or adding a lot to our model, which is very strange, very curious. I wonder if that's the same for learning science and learning reading and so on. Something obviously for you to go and explore. You've seen how we can present results, and the different ways you present results, what you've seen so far are absolutely fine. But as you saw before with correlation, we've got our easy stats. So we need to make sure library easy stats. Let's get that loaded. And then what we can do is we can just write the word report, and I'm going to take the model that I've just done for minutes, wealth, and gender, and I'm just going to report on that model, and it will output, when it feels like it, come on, it outputs a load of text explaining how things are working. You may want to cut this down, obviously, depending on your report, but it's a nice starting point if you want to go and write about multivariate linear modeling. Okay, and that's the introduction to correlation and regression. So let's return to our slides very quickly. We've covered all of this, which means we've covered everything, correlation, regression. So I'm going to now take you through steps to try and replicate the Stoet and Geary report. Okay, thank you. Let's look at recreating part of the gender equality paradox in STEM by Stoet and Geary. This paper was published in 2018 and presents findings that show that in more gender equal countries, girls are less likely to be taking STEM degrees. This they present as being counterintuitive, because you would expect a girl in a gender equal country to be doing, to be able to freely choose what they want to study, and therefore more likely to choose to study a STEM qualification. This doesn't seem to be the case according to the data that they present here. There are criticisms of this, and I highly recommend you have a look at some of those if this is something that you want to go and study. We're going to be picking up on another point that they made, and it's in this highlighted section on this slide. So it says, paradoxically, the sex differences in the magnitude of relative academic strengths. And what that's talking about is it's female academic strength in science compared to the other subjects and compared to boys. So the relative academic strength in science compared to the other subjects, what's the difference between girls and boys? As you get more gender equal countries, the boys seem to be doing better. And again, this might be seen to be counterintuitive, because you'd expect in a gender equal country that there would be a more welcoming environment for girls to achieve in science, and there would be less prejudices against them achieving in science, and therefore you'd expect them to be doing better in science compared to the other subjects. This isn't what the data seems to show, and luckily for us, this data uses this research uses the PISA dataset and another dataset that we're going to be talking about in a second. So this is the graph that we're going to try and recreate, and we're going to try and recreate this finding here. You will see, hopefully, that you recognise some parts of this. We've got confidence intervals over here. We've got a p-value. We've got n, which is the number of items. They've got 62. And you've got something called RS. Well, this is a correlation coefficient. So RS is a correlation coefficient S Spearman. It's Spearman's correlation coefficient. And you're going to see immediately, well, actually, we've got 62 items here. RS suggests they're using Spearman. So why are we using Spearman if we've got 62? We're going to start to see if that's actually the best choice of model for this paper. And I think you're going to see that I disagree somewhat with this, and it would be very interesting to know their thinking behind why Spearman was more suitable than Pearson. So we're going to try and recreate this. You can see that there's a 0.42 correlation coefficient between gender gap in individual science performance and the global gender gap index. So the gender equality of a country, the more it goes up, the more gender equal the country. So Iceland, Norway, Finland, Sweden, your Nordic countries very gender equal according to this criteria. Lebanon, Jordan, Turkey, Algeria, Tunisia, less gender equal. And over here, the gender gap. So where do the boys outperform the girls in terms of their relative strength? So where the boys much stronger at science compared to the other subjects, and the girls are weaker at science compared to the other subjects? Well, Norway's got the biggest gap. And then you've got, it looks like Costa Rica, New Zealand, Iceland, Czech Republic, and so on, are making it up. They've got a line of best fit going along here, which is a regression line, and that does imply that there is a relationship between these two things, and it implies that there is a significant relationship between these two factors. So, luckily for us, Stoet and Geary have published a methodology. So let's take a look at how we can recreate this in R. We have a couple of libraries, or I should say packages, that we need to load. We've got Arrow, we've got Tidyverse, and we've got ggRepel. So Arrow is going to allow us to load our PISA 2015 dataset. You'll find the code on the website. And gggi is actually a CSV file, so that you can load directly with R. Tidyverse is going to allow us to do our left joins and our dplyr statements, and ggRepel is going to allow us to put labels on our graph. So first of all, what we're going to do, we've got 2015 loaded. You can see it here. We've got about 519,000 students on that. GGI, this is our Global Gender Equality Index, and you can see the various countries here. We've got Iceland, we've got Finland, and you've got the overall score over here in the rank. We're interested in the overall score, and we're interested in the country. And we're going to try and match the country and the overall score, and we're going to try and link them to the PISA 2015 dataset. So the first thing when you're looking at this statement here is we're going to left join. I want to left join the PISA dataset to the GGI dataset by CNT equals country. So CNT from PISA 2015, which is from Albania, will match to the Albania in the GGI if it exists. And Iceland will match to Iceland, and so on. So with PISA 2015, I just want a subset, so we go to select. It's just going to select my my country, my gender, because we need gender, maths, science, and reading scores, and science efficacy score. You don't really need all of these. You could get rid of that, for example, but we do. So we do need these because we're going to be looking at the relative score. So our science score compared to other scores, and the GGI index. We just want two things. So we want the country, the overall score, and you've got here 136 countries with the overall GGI index score. By the way, this is from 2015. Stoet and Geary used the 2013 data, and that might make some slightly different results. So, step one. This is what Stoet and Geary say. Let me move this to you. We standardise the mathematics, science, and reading scores on a nation basis. We call this new standardised score Z Math, Z Read, and Z Science. Standardising scores, what that means is it looks at a score on a nation-by-nation basis in relation to the number of standard deviations that score is away from the mean. If I go and run this first of all, so I've now linked two datasets together, you can see that I've got for Albania, I've got female students, and I've got the overall Albania score at the end of that. So we've got every single student, and we've got the overall score, which is the GGI coefficient thrown on the end. Okay, so if I go here, what I'm going to do, I'm going to sensibly rename that horrible field to be gender. Then I'm going to group by the country, and then I'm going to go and add these standardized Z value scores. So we'll go run that. You will see now for maths I have Z maths, and Z maths is telling me how many standard deviations that grade is away from the Albanian mean. So 463 for this female Albanian student is 0.582 standard deviations away from the mean of Albania. And the science score is 1.11 standard deviations away from the mean for Albania, because it's 517, and so on. It does that for every single student by country. So let's go let's run that. So that's PISA 2015 Z. Next, step 2. We calculated for each student the standardized average score of the new Z scores, and we call this Z general. So what does this mean? Well, for each student, the standardized average score of the new Z scores. There are 3 Z scores for each student, and they want to have something called Z general, which is basically you add the Z scores together, you divide it by 3. So let's go and run that. Okay. With a mutate, we'll add another column. Taking a little while. Let's go see what it looks like. Now there's a Z general score on the end. So far so good. Then, step 3. Then we calculated for each student their intra-individual strengths by subtracting Z general as follows. Yep, got everything there. Relative science strength equals Z science minus Z general. Relative math strength, Z math minus Z general. Relative reading strength, Z reading minus Z general. Seems pretty clear. How far is the Z maths away from the general score? So they're looking for the your relative strength in maths, and if you look at these here, you can see science is going to be above their relative strength in other subjects, and reading is going to be below their relative strength in other subjects. And if we go and run this, go run it there, you'll see that's what we get. Let's try and make it a bit bigger so we can see everything. Okay, so we've got our relative math score here, and you can see the math score is slightly below the relative score in general. Our science score, as we predicted, slightly above, and our relative reading score is below. Okay, so we've now got these relative math, science, and reading scores, and then we go to step 4. Finally, using these new intra-individual relative scores, which is what we've got there, we calculated for each country the average for boys and girls. Well, what we can do is we can look at the averages of these, but we could also just calculate it from the mean, Z science, Z reading, and Z general, and then just do that against, so math science, reading general, and then just do that calculation again. So if we go and do this, it's going to hopefully give us a score for each country. So for Albania, we've got the Z maths, which is the average Z math score for all students, the average Z science score, the average Z reading score, the average Z general score, and then we just take away one from the other. So take away maths minus general, science minus general, reading minus general, and you're going to get your relative maths, your relative science, and your relative reading for females in Albania, and the same thing for males in Albania. Okay. Which seems pretty good. We've got the GGI still in there too. And then what we need to do is we need to work out, we need to, unfortunately, because we've got males and females on different lines, we need to try and put these next to each other so we can work out males minus females. And we use pivot wider to do that, which is a bit of a nasty command to have to run, but very powerful. So first of all, I've just got the males and females, GGI, and the relative science score, because that's what we're focusing on. Then we're going to get the names from gender. So we're going to have, we're going to take gender. We're going to have one column for female, one column for male, and underneath female, underneath male, we're going to have the relative science score on both. So if we go and run that, let's just show you that bit. It goes and makes female and science with the GGI index there. And then what we need to do is we need to do male minus female, because that's what they plotted. So we go run that, we get PISA GGI diff, and it looks like this. So for Albania, Algeria, Argentina, Australia, and so on. You will notice here, unfortunately, Argentina, I don't think it's the whole country, so we can't do the match to the GGI score. So we're going to have to dump the Argentinian data. For China, that's not the whole of China. There's certain regions in China. So again, we can't do the match to the GGI. We're going to have to dump that. And there are a couple of countries where I'm going to lose when we try and run this data set. So if I go and run that, we've got our PISA GGI difference, and now we can start to think about plotting this. So the first thing that we're going to do is we want to go and recreate the Stoet Geary. Let's have a look here. We're going to try and recreate this lovely graph here. Let's see how this is done. So back to our code. Well, we're going to plot the GGI difference, PISA GGI diff, with going across is going to be the relative science score, so that's our difference, and then going up was the GGI score, which is what they had as well. And then if we go and plot that, just those couple of lines, you will see that we've got different countries. Okay, that looks okay so far. It's kind of looks like what we're looking for, the model that we had. We're then going to go and add a smooth line. I'm going to leave the error bars on there too. And that again is looking pretty similar. Then we're going to use the geom text repel, which is going to add labels to these things. But if the labels get too close to each other, they're going to repel each other, which is quite useful. So I go and run that, and it takes a little bit longer. Come on. And it actually, if it can redraw. Come on. It's a little bit slow. It redraws it, and it draws lines for the ones where we can't get the label close enough to the dot. But that is looking like a pretty good rendition of what Stoet and Geary had in their paper. And finally, if we want to go and add it, we can add a nice label on the bottom, which is a bit closer to theirs. Now notice, I'm using PV1 Science, and so there are a couple of differences between our model and their model. Their GGI is using 2013, we're using 2015. They're using PV1, 2, 3, 4, and 5 averaged, I believe, while we're only using PV1, so they might get some slightly different, relative different scores because of that. But I suppose the general trend should look pretty similar. So Stoet and Geary used the Spearman's row test for their correlation coefficient. Let's go and see if that makes any sense for our data. If we go and run this, so we've got the GGI and we've got the difference. So let's just double check. So the GGI is going to be this set of data. They've got some NAs in there, so we probably need to go and trim that out. And we've got the difference there. So let's go and see. I think with the NAs, it's probably going to pull them out. But what we can do up here is we can say na.emit, and that's going to get rid of all the NA data. So let's run that again. What do we get? Okay, so you can see we've lost Argentina, we've lost China. That should be fine. So down here now, when I go and run this, lovely. That's a nice clean data set with no NA values. Not that that may have made any difference, but just to make sure we've got only the rows that are complete. So if we go and run this with the core test, you see that we've got a row of 0.28. Their Spearman row was 0.42. So there's something a little bit strange going on here. It is a p-value which is also of significance, and as you can see there, they got a much lower p-value than the p-value we've got. So it is a bit weird that we've got a result which does seem to be so different from theirs. But why are they using a Spearman? Well, Spearman should really, on rule of thumb, be for data which has more than, less or fewer than 30 items. We've got in our data sets up here. Let's have a look. How many data items do we have? We have 59 data items. So 59 is well over 30. So you would think that we should be okay using Pearson rather than Spearman. We can also do our Shapiro test. We need to make sure, look at the p-value on the Shapiro test. And is it greater? Yes. So it is greater than 0.05, which means we can assume the normality of the data. So Spearman doesn't seem like the right choice here. Pearson's seems like a much better choice. And let's go look at difference. And again, that's well above 0.05. And it does seem that certainly for our interpretation of this and for the model that we built, that Spearman would be the wrong choice and Pearson would be better. And I just remind you here, so we get 0.287 for Spearman's row. If we go and run the same test with Pearson rather than Spearman, we get 0.467, which is much closer to the result that they found. And our p-value here is again the same sort of p-value that they saw. So I think that maybe that little s doesn't need to be there. Potentially, we have a finding here which suggests that they should have written that this was a Pearson test rather than a Spearman test. It doesn't really call into question the result. The result is a very strong correlation with a very strong significance. So the finding seems to be sound. It just seems that they've potentially reported the finding incorrectly, or our data just isn't replicating it as we wish. It would be lovely to see the original code behind this, so then we could double check. We can also, for the sake of it, go and throw in the linear model. So we can say data equals this lovely PISA GGGI diff, and then on that we can go and throw in a we're going to have GGGI, or difference given GGGI. If we go and run that, what does that give us? Well, it's suggesting that there's something going on. If I go and put this into a summary, we get a model down here which has got a relatively decent R-squared value, and it's got a significant finding for GGGI. So GGGI seems to help predict the difference between girls and boys. So and it's in a positive way. So the stronger, or the more gender equal a country, the better relatively boys are going to do compared to girls in their science subject. So what does this say about the overall finding for Stoet and Geary? Well, I think we support the findings. I think our findings are pretty much in line with theirs. There is a big question here about whether they really did use Spearman rather than Pearson, and it would be really good to find out. It's also another big indicator that we should ideally be publishing our code alongside our findings, even where you have a really nice, clear methodology like Stoet and Geary. If I get a slightly different result at the end, I want to know why, and if I had the original code, I could really explore that and find out why. And our difference might be because we've calculated this D value slightly differently. We've got the PV value, one PV value rather than 5 PV values, as I mentioned earlier, and obviously we're using a different GGGI. So it could be one of those things, but I do have questions about whether the S here is correct and whether this was Spearman or it was Pearson. I think it's looking more like it should be Pearson, and actually the results they've got may well be Pearson. They've just put this in wrongly. But it doesn't really change what we're finding, and I suppose the next thing that you could do is you could go and explore this a bit further. You could go and look at intra-individual math scores and intra-individual reading scores, and you could look at this in 2018 data set as well to see if there are any other factors that have changed this model between the years and between the subjects. You could also be looking at a linear model with more independent variables. You could be trying to throw some other things in there to see if there are other ways of predicting this intra-individual science performance beside the global gender gap index, because there might be some other factors that come into play there as well. And that would be a really interesting finding if you want to go and explore more of this. Anyway, I hope you've enjoyed this overview, and I will catch you again soon. Bye-bye.